In this lesson, you'll learn about 4 other types of organic compounds, how to name them, how to draw them, and we'll briefly talk about some of their properties as we go through the lesson. So today we're going to cover esters, ethers, amines, and amides. They're a little bit different than some of the other groups that you might have learned about so far. But hopefully you're getting more comfortable with drawing organic molecules. So now at this point, you'll see there's a lot of repetition with certain parts of the name, regardless of what group that you're looking at. So like some of the other ones, we're going to go through all of the structure and naming rules, and then we're going to practice naming and drawing. So we're going to start off with an ester. So let's take a look at esters. So first thing, the name ester. The name of the functional group is just called an ester linkage. It's a linkage because it links 2 parts of a molecule together. Normally we have a straight chain of hydrocarbons somewhere in the molecule, but here it's interrupted by another molecule, which is going to be an oxygen. So you've got a carbon, which sits in here. It's got a double bond to oxygen and a single bond to an oxygen on the other side. And then attached to the oxygen here, you've got at least 1 carbon or longer, so a hydrocarbon chain. And then over here, you're going to have either a hydrogen or more carbons and hydrogens attached. Because there's 2 parts to this, you're going to see 2 parts with the name. So let's take a look at how this works. One part has to do with what is attached to the carbon with the double bond to oxygen. That part, when you make an ester, comes from the root of a carboxylic acid. And we know we normally name carboxylic acids with the suffix oic acid. So instead of having oic acid, it's going to end in OATE. So that part is the part from here, and it goes attached here the way this diagram is shown. The other part is considered an alkyl group, or like a branch, and it's the part that's attached over here with that oxygen. So we just name it like a methyl or an ethyl or a propyl. It doesn't matter, whatever its length is, you count outwards and you put its name together. Then you put the branch name and then you end in OATE. Here though, one thing that's different is it doesn't matter which side is longer. We've talked a lot about length of chains. This branch could be longer than the part attached to the double bond to oxygen. That doesn't matter here. The 2 parts are distinguished by what is attached where. So one part with the carbon to double bond to oxygen, and then the other part with the hydrocarbon chain attached to this oxygen here. Okay, next let's take a look at ethers. Ethers are probably the one that's different from most others. So how does it work? First, the functional group is called an alkoxy group. Alk for alkane, or like the hydrocarbon, so carbons and hydrogens, and oxy for oxygen. So here you've got an oxygen, and attached to it you've got 2 carbon-carbon bonds. One of them will act like the alkoxy group or branch. When you get an ether, you have to count how long the carbon chains are on either side of the oxygen. So count over here and count over here. If one is longer than the other, the longest group becomes the base chain, or the root of the name. The other one, the shorter one, then becomes the alkoxy group. And you're going to change that ending. If we had a normal branch, it would be YL, but instead of YL, it will end in oxy. You also have to identify, just like any other branches, where the alkoxy group is attached to the base chain with a number. So is it attached on carbon 1, 2, 3, or 4, or whatever the number is? So you need that number in there. And then putting it all together, you need that alkoxy branch name, the alkoxy group name, and then you end with the base chain. Next up are amines. Amines have nitrogen in them. We haven't seen nitrogen be introduced yet in terms of structure. Uh, in an amine, we have the amino group for the functional group. And there's three ways you can see the amino group being represented. The first one up here is called a primary amine. The second one is secondary. And the third one is tertiary. Why do we do that? If we start looking at the structure, the first one, if we expand it, looks like this. This is primary. Primary amine over here has one bond to a carbon, and then it'll have two bonds to hydrogen, and then there's a lone pair of electrons on nitrogen. So the primary part comes from attached to one carbon over here. A secondary amine will still have that we'll have that lone pair on the nitrogen, but it only has one bond to hydrogen. So it will have a bond to carbon here and here, and then one bond to hydrogen, and then that lone pair. A tertiary amine, and you might guess the pattern by now, has no bonds to hydrogen. It will have three bonds to carbons. So in terms of the functional group, they're all called amino, but because of what could be attached to that amino group, the properties of amines can change. So for example, if you look at a primary amine, it's going to be one where you have a more polar group. There's hydrogen bonding that can happen here with the nitrogen and hydrogen two places. With a secondary amine, there's one opportunity over here for hydrogen bonding. Over here, tertiary amine can't make any hydrogen bonds. It might accept one with the nitrogen, but it can't make any on its own. It has nitrogen and carbon. So down here is only dipole-dipole forces, whereas these two have some hydrogen bonding. So in terms of properties, a primary amine would give more polar character if you're looking at similar length hydrocarbons in that group. So how do we deal with this one? So first thing you need to do, find the longest alkyl group, and it's going to be the base chain. So if you've got more than one carbon attached, whichever one is the longest becomes the root name. For primary, you'd only have one attached, so it doesn't matter. That automatically will become the root chain. If it normally ends in ANE, if you named it like a hydrocarbon, get rid of the A, and you're going to put on amine at the end. Now, if you have a secondary or a tertiary amine, step 3 only applies for secondary and tertiary. What you're going to do is name the alkyl groups that are attached to that nitrogen atom, like methyl, ethyl, propyl, whatever that is. But because it's attached to nitrogen, you're not going to use numbers this time. It's a little bit different. In place of a position number, you're going to use a capital N to indicate that it's attached to the nitrogen and not part of the hydrocarbon chain. When you put it all together, you're going to put any branches first, if there are branches. So name the alkyl groups. Then you're going to put the base chain, and then you're going to put amine at the end. Now, the other thing you might find is the amine might not be attached at the very end. It might be attached somewhere in the middle. So if it's not attached on the end, you also need a position number to indicate where that amine is attached. Last one up are amides. Amides are similar to amines, but it's a little bit different. So when we look at the functional group to start, an amide group has a carbon with a double bond to oxygen, and it'll have a single bond to nitrogen showing that amino group on there, but this carbon has to have both attached to it to make it an amide. This is an example of a primary amide. Primary because here you've got that amino group attached, and it is bonded to one carbon here and two to hydrogen. A secondary amide follows the same principles if we were looking at primary, secondary, and tertiary amines. Here you would have your amino group, but then it would be attached to another carbon chain. And then we normally don't show the electron pairs in there, but it's sitting in there. And tertiary would work the same way. The carbon with the double bond to oxygen always has the nitrogen attached, but this time you're going to have different hydrocarbon chains attached to it. If you look at their properties, comparing the three, primary amides are the most polar functional group you'll see. So if you were comparing chains of similar size of different types of organic molecules, if you had one that's an amide, it's going to be the most polar. So it'd have higher melting point, higher boiling point, easier to dissolve in water, and so on. So you've got that double bond to carbon here. Here you've got the dipole-dipole forces forming. You can also have hydrogen bonds coming in here to that oxygen. And then down here with that amino group, you have those opportunities for hydrogen bonding. And this bond in here is also polar. So overall, this is the most polar functional group that you'll find, primary amide. It gets trickier when you get into secondary and tertiary, when you start comparing like a carboxylic acid, for example, and a secondary amide. They're very similar in their polarities and also depends on other factors like chain length. But if you're comparing something that's similar length, you can confidently say that that primary amide would be the most polar. So this one also has two parts to the name. One part works very similar to the ester. One part is going to start with that carbon double bonded to oxygen, and it's going to make the base chain. So this carbon here is always carbon 1, and then you're going to count out from it to find how long the chain is. The ending here, instead of ane, if it was just an alkane, changes to amide. The other part has to do with what's attached to the amino group. So if you have side groups attached to the nitrogen, those are going to be the branches. And just like amines, you're going to use an N to indicate that they are attached to the nitrogen, and then put their regular alkyl name like methyl, ethyl, propyl, and so on. And all of those other rules apply with alphabetical order with branches and so on. So now what we're going to do is take some time to put all of this together and practice some naming and some drawing, and then you'll be able to get an opportunity as well. So I'm going to walk you through 4 examples, and then I'm going to ask you to pause and try the other 4, and then we'll take a look at the answers together. So just like any of the other molecules, the first thing you want to do is try and identify what type of molecule you have. So ignore all the carbons and hydrogens, what is different. When you look here, you've got carbon double bond to oxygen and a carbon single bond to oxygen. So in here, this is your ester linkage. Once you know you have an ester, you have to think about the naming rules. There's 2 parts to an ester. One part has to do with what's attached to the carbon double bonded to oxygen. This is going to be your base chain or your root chain. And then the other part is the part that's attached to the oxygen over here. This part over here is going to be your branch. If you imagine the 2 parts, you kind of cut a line right in here, and there's one part and there's the other. So if we start with the branch, because it always comes first, 1, 2, 3, we know that's propyl. We named it as a branch. And then the second part of the name, we have to start counting from here. This carbon always counts, don't forget about it. 1, 2, 3, 4, and 5. So this is a pent base. So we're going to change the ending to OATE. This one is a little bit different. It actually has a space between the branch and the name. So propyl comes first, leave a space, pent for 5 carbons, AN because all of the carbon-carbon bonds are single, and then put OATE for O8. Okay, so that's our first one, an ester. Now let's try another example. Down here, we've got an example that's different. We see nitrogen is in here. Only difference here, carbon, hydrogen, and then nitrogen. So we have to decide. We know with nitrogen, it can be amine or amide. This one is an amine because there's no carbon with a double bond to oxygen. If you see nitrogen and that carbonyl group combined, you know you have an amide. So then we have to see how many groups are attached. Okay, I've got nitrogen. This carbon chain is 2 carbons long, and this carbon chain is 1 carbon long. So I have 2 parts here. This would be an example of a secondary amine, just for reference. This is the shorter length of the two, so this is going to become my branch. The longer of the two becomes my base chain. When I want to put it together, branch comes first. But again, since it's attached to the nitrogen, we're not going to use a number. We're going to use the capital letter N. So attached to nitrogen, I have a methyl branch. And then here, there's no spaces. We continue on. My base chain is 2 carbons long, F. AN for single bonds. And then I put on amine. You could have also put a -1 in here, right between the AN and the amine, because it's attached on number 1. But usually, like number 1, we leave that number out. Let's take a look at another example. Next example down here, when we look, the only thing that's not carbon and hydrogens is an oxygen. But here it's single bonds between carbon and the oxygen. So that tells us we have an ether. Now, ethers are a little bit different because they can look a little confusing. So, first thing we need to do is count how long these two chains are. This chain over here is 1, 2, 2 carbons long. Then we have to see how long this chain is. We can count from this end or this end. I could go 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5. So we know this is 5. It's the longest chain, but which way do I want to number? I want to put the oxygen attached to a carbon with the lowest number possible. So if I count like this, it's going to give the attachment where the oxygen is on carbon 2. If I counted the other way, this would be carbon 4. So I want to go like this to make sure it's number 2. This over here, this is your base. And this over here is going to become your alkoxy branch. So the alkoxy branch is what comes first in the name. Here we can see it's not attached at carbon 1, it's attached at carbon 2. So I have to indicate that with a name. I'm going to put a 2 to say my alkoxy branch is attached at carbon number 2. It's 2 carbons long, so I use eth. But here, instead of putting ethyl, I have to add in oxy, because oxygen is part of the branch. This is the entire branch, from the oxygen to the carbon. So a 2 carbon branch with an oxygen attached to it, and it's bonded to the main chain at carbon number 2. Once you've done that, the rest of the chain is just like naming the alkane. No spaces here. Pent for 5 carbons. AN for single bonds. And then it just ends in E, ANE. So 2-ethoxypentane. Last one up is down here. So let's take a look again. What type of compound do you think you have? When you take a look here, here's your functional group. This is telling you an amide linkage. So again, with an amide, just like an ester, there's two parts. This is one part over here. This is going to be your branch. And then the other part, starting from here, all the way over here, is your base chain. Our branch is 1, 2, 3 carbons long, so it's a propyl branch. Our base chain, we count 1, 2, 3, 4, and 5. Now you might notice on the base chain this time, there's also a branch. So you can have a branch on the nitrogen, and you can have a branch on the base chain. That's okay. We're going to put all of the branches out at the beginning. So this is a methyl branch. This is a propyl branch. So M is going to come before P alphabetically. Here we're using numbers to indicate it's attached to the base chain. Over here we're going to use N to indicate that it's attached to the nitrogen. So it will tell you the differences in the names here. So we're going to start. 4-methyl comes first. Then comes the branch attached to the nitrogen. So just same format, except we're going to use N. 4-methyl N-propyl. And then we put the base chain, 5 carbons, AN for single bonds, and amide. So 4-methyl N-propyl pentan amide. Okay, so that walks through an example for each of the 4 groups. Hopefully now you have an idea how this works. So there are 4 other examples on the other side of the notes. I'd strongly recommend that you pause the video, have a look at the notes, and try to identify what group these belong to, and then try and name it. It's the best way to learn if you try, and then we'll take a look at the answers. So give the video a pause, try them out, and then we'll walk through the answers together. All right, let's check some answers here. So hopefully you found the answer to the first one. Over here, it's an ether. This part down here is your alkoxy branch, 1 carbon long, so it's meth. We call it methoxy. It's attached at carbon number 2. The base chain is 6 carbons long. So when you look here, there's also another side branch here, which is why you see 3-methyl down here. And then hexane, ANE for all single bonds. Let's take a look at the next one. The next one, hopefully you identified as an ester. So why is it an ester? Here's that ester linkage in the molecule. Over here, it's 4 carbons long. Here's a branch on that chain there. And here is your branch attached to the oxygen. Again, if you see a branch out front with a space in it, it implies that it's attached to that oxygen in there. Any other branches that you see attached to the name will have numbers and they'll go with the base chain. So this 3-methyl is this group up here. The whole chain is 4 carbons long with single bonds and then OATE for ester. Next one up. Here is the name. This is an amide. So here's your amide linkage, carbon double bond to oxygen and a nitrogen. But here there's 2 groups attached to the amino part of the group. You've got an ethyl and you've got a methyl. So ethyl comes first, N-ethyl, then N-methyl, 1, 2, 3, prop and amide. Let's take a look at the last one. The last one down here is an amine. So when we look here, this one is a tertiary amine because there are 3 carbon groups attached, 1, 2, and the third one here. These 2 over here are shorter in length, so these are branches. This chain over here is your main chain. Remember, you have to count to see how long it is. So it's 3 carbons long, but what you might notice here is the nitrogen is attached at carbon 2. So we need to make sure we indicate that in our name. Since both of the branches are both methyl, you group them the same way you would like other multiple groups, except you use 2 N's. So NN dimethyl are for these 2 groups. Prop and are for 3 carbons here, all single bonds. But then you have to put the 2 in to say where is that amino group attached? It's attached at carbon number 2. So that's referring to that position right in there. Next, what we're going to do is draw some molecules. So we'll do the same thing. We'll walk through a few examples together, and then you'll have an opportunity to try and do some yourself, and then we'll check to finish the lesson off. So here I want to think first, what group am I dealing with? I see OATE, and this is making me think, okay, ester. So with an ester, I have that carbon double bonded to oxygen and a single bond to oxygen. This is usually a good place to start when you're thinking about drawing. What does the functional group look like? So for an ester, I often draw it first. So carbon double bond to oxygen, and then I can put the oxygen on the left or the right. It really doesn't matter which way you do. So let's say we put it on the right. The first part of the name is the branch, and it's going to be what's attached to the oxygen. Propyl is 3 carbons, so 1, 2, 3. There's the propyl part of my name. Then I have ethanoate. Eth means 2 carbons. This is already 1 carbon, so I just need to add 1 more. So 1, 2, and then this is my branch here. So this is the main chain, and this is my branch for reference. Next, 2-methoxypropane. If you see that oxy in the name, then you have to think this is an ether. Ether means oxygen with carbons bonded to it. With ethers, usually what I like to do first is draw the base chain, so the propane chain. I can see that there's something attached at number 2 on my propane chain. So CH3, I'm going to have my group attached on number 2. So I'm going to leave a spot for bonding. Meth means 1 carbon, so I know the oxygen has to be bound at number 2. And then attached to this, I'm going to have my methyl group. 1, 2, 3. Number 2, there's my methoxy branch, and the propane is my main chain. Next up, pent-N-2-amine. I see the word amine, so I know I have an amine. These ones are nice. The name tells you the group. So, pent means 5 carbons, all single bonds, and attached at carbon 2, I have my amine group, my amino group. So, carbon 1, carbon 2 is going to have an amine group. And this is a primary amine because I don't see any branches with the letter N here. So I know it's going to be NH2. And then I just continue on my chain like this. Last one, I look at the name NN-dimethyl-2-methylbutanamide. Lots going on here. So first thing I see, I've got amide, and I see two N's in here. That's going to tell me right away I've got a tertiary amide. So when I draw this one, just like an ester, I like to draw the group first. So carbon double bonded to oxygen, and then I've got a nitrogen. It can go on either side. It doesn't matter. I know my nitrogen has to have a pair of electrons. I like to put that in sometimes just to remind myself not to put an extra hydrogen in. And then I know I have to have groups attached to my nitrogen. So when I look, I've got two groups attached to the nitrogen. They're both methyls. So this is one of them, and this is the other. Then I go and look at my longest chain. 4 carbons, but I've got a methyl on number 2 of the main chain. This is carbon 1. This is carbon 2. I know I have a methyl group attached to it. Carbon 3 and carbon 4. So 1, 2, 3, 4, like that. So going through those 4 examples, hopefully that helps you identify from some of the features of the name what families you're dealing with and how to start drawing them appropriately. Like the last time, there's 4 other examples for you to try drawing from the names. So pause the video, see if you can draw them, and when you're ready, press play and we'll just walk through the answers together. Let's take a look. Here are the first 2. Ethyl 2-methyl pentanoate. So again, OATE means ester. So I've got ethyl here. That means that it's separate from the rest of the molecule. It has to be attached to the oxygen. 1, 2. That's this part of the name here. I've got pentanoate. 1, 2, 3, 4, 5. That's my long chain here. And on that long chain, I've got a methyl at number 2, which is why it's sitting in here. Let's take a look at the next one. When I look at the name, everything sounds like hydrocarbon, except for that one little bit in here, ethoxy. If I see that oxy in there, I know I need my ether. Now this one's a little bit harder. It's got a little bit more going on. So where's my pentane chain first? 1, 2, 3, 4, 5. There's my pentane chain. Attached at number 3, which is here, I have my ethoxy group. 1, 2, and this oxygen in here, that's ethoxy. Next, I have 2-methyl. The 2-methyl is referring to this group attached here. I have a methyl branch on carbon 2. Even though you've got an oxy branch and a regular branch, all the rules still apply. E comes before M alphabetically, which is why you see the ethoxy listed first. Last 2, we've got N-ethyl propanamide, so we know this is an amide. Prop for 3 carbons attached to the carbon with the double bond, so that's this one over here. And then this is the N-ethyl, 1, 2, and here's the N. So this is my N-ethyl. And this here, if we're looking, this is an example of a secondary amide for reference. Last one, N-ethylbutan-2-amine. I see amine, so I know amine or nitrogen's in there. I start with my longest chain 4 carbons. 1, 2, 3, 4. I've got an ethyl attached to the nitrogen, but I need to know where's my nitrogen attached. My amino group is attached at number 2. So here's carbon 2. Here's my nitrogen. It's not shown here, but we've got those 2 lone pairs. 1 bond to hydrogen, and over here is your ethyl group, 1, 2. So this whole thing over here, that's your N-ethyl part of the name. So just like the others, these take a little bit of time to practice, but hopefully taking some of your knowledge you've learned so far about organic molecules makes this a little bit easier. So trick is lots of practice, naming, drawing, and start again to thinking about properties when you run into those types of questions.